Okay, and so thank you. I look forward to another 2 afternoons of interesting talks and engaging discussions and stimulating thoughts. And speaking of statistic wars, I'm also quite delighted that Daniel Lakens is chairing the session today, because as you can see in these tweets that we exchanged earlier this year, he thinks very highly about my work. He literally defined K-theory, which is part of what I'm going to discuss today. In fact, the bigger part, to be fair, incoherent nonsense. And what's worth, I'm entirely biased for it. So that's going to be a problem, I suppose, in this whole talk.
Okay,
and
thanks.
Even though, to be honest, I didn't get it, with one exception that, if I remember, I'll mention a concrete, specific feedback about what exactly is wrong with what I'm saying. You're warned that this might all turn out to be a new so-called hoax, maybe 10 years from now. But hopefully I'll reveal it later on. So I'll just say that I look forward by the end of this talk to either see the chair recounting his position or giving me more such constructive and helpful feedback like this. And for the rest of the audience, I hope that I'll give you elements to make up your mind as to whether this is all a hoax or maybe there's something to it. And in this talk, I have 3 fundamental objectives. I want to outline and articulate what I think is missing, and certainly how we do meta science. So how we do meta science, but also I would argue at least areas of statistics and in fact research in general. And then by means of illustrating what a solution would look like, I'm going to illustrate what the solution I'm proposing looks like, which is this K-theory that we already mentioned. And in the third part, I'll give some evidence in support of it. And with the overall premise that whilst, again, based on the evidence that I'll show you, I do believe that this is an encouraging path to take. I'm not necessarily, well, in fact, I'm quite open to the possibility that there is an entirely better way to do what I'm suggesting should be done. And so at the very least, a take-home message of this talk is going to be that there's a proof of concept that the problem that I will illustrate in part A is solvable, and in other words, complexity can be measured and integrated into research. So I'll be talking a lot about complexity. What do I mean by something being complex? Well, basically, you might look at complexity science and think that people sort of still haven't agreed upon exactly how we measure complexity or what it means, etc. But in reality, there's a fundamental way that we can all understand what a complex object or a system is. It's something that has many diverse interacting parts. And an equivalent definition to that is to say that such an object or system is going to be longer to describe and its behavior harder to predict. So just to make things a little bit more concrete, as in fact might become clearer even later, but there's a very apt way to describe any system or object in terms of a graph, by which I mean a set of objects, okay, and these are the parts and interactions between them that we conventionally represent as edges or arrows essentially, or lines. And so in this schematic example, complexity increases as we have more stuff going on and more diverse stuff going on. Now, slightly less intuitive on the point about description is that you can have an object such as the first one on the left in the lower row, that might appear in a certain sense to be complex, but it's actually homogeneous and very simple to describe. Just take n objects and connect them all in the same way. So that is actually a sort of a simpler object than the one in the middle, for example, which has a more idiosyncratic set of connections. And of course, again, if you start to consider diversity of connections and entities, things get more complex. So this is the fundamental sense in which certainly I think about complexity, and I think it's sort of apt to capture the fundamental problem that all areas that deal with complexity face. Why am I saying this? Because my next argument is that there is a big complex elephant in the room, or a complexity elephant in the room. And it's a complexity elephant because, as you can see, it's at the moment at least constructed as a very cryptic graph. And what is the problem with this complexity elephant? Well, basically, because complexity is an obvious confounding factor in everything that is being discussed, certainly in meta-science as well as in many other areas, but for one reason or another, it is never formally addressed, really, with a few exceptions that actually we will discuss. And so, in fact, what I originally intended to do for this talk was to articulate many more examples, actually, of where this issue of complexity comes up and is brushed under the carpet. Then I realized that half an hour only has 30 minutes in it, and so I had to cut short the examples and really focus on the two for which I have data sort of to show and show concretely what a solution looks like. And so my examples now are going to be on meta-science, and in particular reproducibility, and statistics, and how that deals with model complexity. But I did discuss, for example, some more of these examples in a seminar that I gave for Stats Wars last year. And of course, there are a couple of papers that I'll mention at the end. I'll give references at the end where you can find a little bit more, and there might be more opportunities to mention other issues. So the first example, complexity and reproducibility. Well, as some of you might know, I've become a counter voice and indeed a skeptic of the whole reproducibility crisis narrative that, of course, is still sort of props up here and there in these discussions as well in this particular workshop. And well, the fundamental reason is that I look at the data, and this is the best data that we have that estimates reproducibility by taking samples of papers from different fields and basically has different labs trying to replicate it. And I really don't see the issue here. And I don't think anybody who would look carefully at the data actually would see the issue. Before I get there, I'll mention a couple of things that I won't really be discussing here, but have to do still with complexity. So one, you see these percentages, which are the percentages of successful replications. Like now, many people, and I am totally with them, say that this is an entirely flawed way to measure reproducibility in the first place, because we are dichotomizing something that isn't dichotomic. In fact, the data shows very well that rather we have sort of a degree of decline in effect sizes. So if anything, we should measure reproducibility in relative effect sizes in some kind of rescaled measure like that. And this is something that I did discuss in the seminar last year, and in fact, I have sort of my own measure proposed there that I won't be discussing here. The other thing to notice is that for most of these studies, we get ranges of measures. Why do we get ranges of measures? Because even accepting this flawed premise that we're trying to determine which replications were successful or not, we don't really know how to do it. And what we do is that we sort of try a variety of methods, which means essentially applying different criteria, but primarily different arbitrary thresholds, be it the p-value, be it confidence interval, predictive intervals. Maybe a meta-analysis is a little bit more sophisticated, but still with the optic of saying, well, does it or not overlap with zero, etc. And depending on the methods tried, people have come up with, in some cases, widely different estimates. And so there's a measurement problem here that, again, I would argue is part of this this issue of trying to brush under the carpet the real complexity of the matter and trying to get some binary answer. Now, this is not really what I want to focus on. Instead, my real problem is that even if you embrace all of these limitations and sort of criticisms and take these measures as valid, you will have noticed how all, at least the upper estimates, and in fact, in most cases, all of the sort of the full range of estimates obtained is well above 50%, and in fact, so in some cases, fairly high, at least compatible with a very high estimate. And so why on earth are people who know this evidence saying that there is a crisis here? Now, to be very clear, I think a lot of people actually don't know this evidence or haven't particularly done their homework and engaging critically with it. They just take this narrative for granted. It's been a hot topic, and we all know that. It has led to a lot of interesting research, and so don't get me wrong, I love these studies, and this data is fantastic because it's a whole new way to really study science itself, and so I'm grateful to the narrative. But nonetheless, had people critically engaged with this data, I don't think they could have come up with a conclusion that there is a serious problem unless they assume that reproducibility should be 100% across all fields, or 95% or something like that, which doesn't make any sense for arguably any field. But I think it's quite intuitive, not controversial at all, to say that at least some of these areas presumably would have greater problems on the face of it at least, to replicate than others. If anything, and this is not necessarily the only argument, but basically because they are dealing with phenomena that are more complex and use methods that are necessarily more complex, by which I mean that there are many more variables, many of which perhaps we don't know, for example, especially in immature areas of research and new fields. No, there's a lot that we still have to understand as to how these phenomena work and what we need to control in an experiment to measure results, etc. And so there are lots of unknown unknowns. And this is not just random noise. So the meta-analytical solution of assuming random effects and going by that, which some of the participants to this workshop in part advocate for, has its place somewhere, but it's not like the panacea to solve the problem of complexity, because much of the problems lies precisely in the fact that this is not random noise, it's structured noise in a sense. It's structured aspects of reality that we are unable to account for. Now, the second example that I will elaborate upon is that of statistics. What's happening here? Well, statistics is one of the few areas that tackles complexity explicitly. However, here the problem is that the concept of complexity typically addressed in statistics, and that indeed is how many people would define complexity, at least for a statistical model, is purely in terms of the number of parameters that a model estimates. So most famously, many of you might be familiar with the Akaiika information criterion, which is one of the most elegant ways by which one goes about evaluating the strength of evidence for a particular statistical model by basically penalizing the log likelihood, the negative log likelihood, more exactly, by the number of parameters estimated. So ideally, one wants to minimize the Akaiika information criterion by getting the lowest possible, again, negative log likelihood, or the highest log likelihood, either way, with the smallest number of estimated parameters in the model, which makes the model certainly simpler in a certain sense. But what is the problem? That we understand that that's not the whole story, that there have been a few studies, and for example, the study by Bonifay and Kai in 2017, that shows explicitly how you can take 5 models, as they did here, 5 structural equation models, over the same number of parameters. You generate random data, basically, in fact, in this case, you generate the full spectrum of data, represented here by the area of this square, and you just fit these models and see how many successfully fit the data. And there's a sort of some arbitrariness around the criteria that you use, but basically you see differences, okay? And we'll get back to this example more in detail later on. But this is a fundamental problem. Why? Because, of course, statistical models are supposed to give us evidence for theories and hypotheses. And so if it so happens that your theory is implemented by a model that just by virtue of its shape, its structure, it's better able to fit any random data, then the support you think you've obtained for your theory is actually weaker than you think, right? All right, and so how would we start to make this elephant appear? Well, fundamentally, what I would be advocating for is a methodology to integrate this aspect of complexity of phenomena or of methodologies, etc. For example, in how we measure, forecast, or correct for reproducibility. And then in statistics, similarly, the solution must come from some way of further penalizing the fit of a model by this other aspect of model complexity, i.e. the fitting propensity, regardless of the number of parameters. And I'll just throw out here as a consideration for general discussion is that what I have in mind here, without saying that it's the same thing, but it's very much aligned for this idea of severity of testing that has been expounded, in fact, by a few talks already previously. So the spirit here, I think, is very much the same for many of us. And so now, what does a candidate alternative look like? And this is going to be my proposal. As I said before, I'm not going to say that this is necessarily the ultimate proposal. So the elephant sort of starts to have some flesh on it. It starts to appear and emerge from the darkness of the room. I'm not saying necessarily that this will be the elephant that we will see at the end. And the way I think we can go about doing what I just described is with what I call K-theory, basically with inferences derived from conclusions derived from this K function here. This is a function derived theoretically, and in the seminar I already mentioned in Stats Wars, for example, I did describe a little bit more how it is derived. I won't bother doing that here. What I hope to give you now is a more intuitive sense of what this function means, what this K number means. And it's a measure of consilience, fundamentally, i.e. the ability to explain, predict, or control more diverse phenomena using fewer and simpler theories and methods. And this, in my understanding, is sort of the best definition we had, and it's a very old one, by the way, of what science is. And in fact, I would argue it's not just science, is all of knowledge. Indeed, it's arguably all of sort of biological adaptation. Okay, it's the whole point of natural selection in an ultimate sense. This is why I think this is a sort of an important, profound concept. And K, without having intended sort of necessarily in its derivation to do this, but embodies exactly this concept. And it translates each of these elements of the definition into a quantity of information. So these H functions and D functions gives us bits of information, with the exception of the N that are actually just integers. But basically, the orange is the information of the phenomena we are hoping to have information about. The green is the information that we remain without in trying to explain or predict them, and blue is the information that it costs to encode essentially our explanations and models and theories and methodologies, etc. Right, so simply this is a number that is going to grow the more information we have about some phenomenon or many phenomena, and it's going to decrease the more, again, we're doing a bad job at explaining, predicting, etc., and or we do it with very complex theories and explanatory structures. And it can be one, it can be many. Again, the mathematics are exactly the same. What we get is a number that asymptotically reaches 1, the better we are doing at consilience, fundamentally. If the answers that we get, the explanations we get are random, we have a K of 0, and that's no knowledge. If we get positively wrong answers and our predictions are the opposite of what we observe, then our K is negative, and we can potentially be infinitely wrong, in fact. That said, I won't be discussing the latter at all. But what I want to give you next is an example of what would go into this K number, making one of the simplest possible instances of scientific knowledge, which is a regression model. I presume you're at the Stats War, you're all familiar with how that works. We have a response variable, response variable Y, intercept alpha, beta slope, X explanatory variable, and some residual error. And well, basically, the entropy of the response variable with the null model, essentially with no explanation, is what would give us the orange bits, okay, the explanandum, as I call it. The entropy of the error term is what would give us the residual ignorance, as I call it, the green bit. And notice that if we were to stop here and just have the orange and the green bits, then we would have something that already exists in the literature. In statistics, for example, not quite in this form, but in something that is quite analogous, it would be a pseudo R squared that some have proposed as a measure of fit for regression models, once one uses maximum likelihood estimation. But for example, I found it in a book that was trying to explain evolutionary biology in terms of entropy. Or, for example, someone pointed out after I published these ideas in 2019 that there was a paper from a sociologist who used this, again, orange and green bits only, suggesting this could be a measure of knowledge, interestingly. But again, what I'm claiming is something that goes beyond that, and purely from a theoretical derivation, which is that there are the blue bits there. So to measure knowledge, we actually also need information that in this particular example would entail having the entropy of the explanatory variable and some measure of the complexity of the structure of the model. And that is the blue bit here. So this is sort of the key innovative part that gives rise to all sorts of different conclusions and derivations. And from a methodological point of view, the novelty, and particularly with a breakthrough that I published earlier this year, is that I claim there is a universal language, which is a graphical language, a particular type of graph, a nested hypergraph, that we can use to translate any structure, including this regression model, into a graph, basically, that from which applying just this D function, which is a sort of a mechanical function, it will give us the number of bits that we need. And beyond that, all I'm saying is that this is doable not just for regression models, it's doable for any kind of theory, or any kind of methodology, at least to the extent that you can describe it as a graph. And the fact is that we already do describe both theories and methodologies as graphs. Okay, theories, we do it quite formally in some cases, such as in structural equation models, but also informally. And I think, in fact, that there is a profound reason why this is the case. I think that graphs capture something about how our consciousness works, how our cognition works. And so it is no coincidence that graphs are the universal language that we need. And it might be less obvious that we can use graphs in methodologies, but there is a whole startup called protocols.io that some of you might know that collects protocols from users and encourages them to use a graphical language. So not as strange, I think, as some seem to see it. And that said, again, this is not just some idea, it's an idea that increasingly seems to work. So this is why the elephant now is sort of a little bit more boldly coming out of darkness, but I'll concede that we don't have the full picture there, and maybe it's just the wrong one. And there's another elephant somewhere else, better describable and more, well, the real elephant that we need to describe. Stepping outside of academic metaphors, let me get to the two key bits of evidence. So first of all, with regards to reproducibility, there is evidence that K, so this whole methodology I proposed, might predict how we perceive as well as how we actually sort of will measure reproducibility in studies. The perception part was actually already published earlier this year in a preprint. And this is part of a collaboration with the Brazilian Reproducibility Initiative, who is going to replicate 60 biological experiments. And what we did, in fact, just about a year ago, was to take the replication protocols that they had and I simply devised, after some trial and error, a suitable descriptive scheme, and basically constructed, sort of derived tau graphs from it. And so what you see here is one such nested multi-level hypergraph. Okay, the multidimensionality might not be obvious because these are obviously two dimensions, but believe me, it's there. And the blue lines that you see there, that's the text of the protocols that ultimately simply gets passed into self-contained concepts, and these form the nodes of the graph. All right, so you apply the D function to this, you get the D of tau. Other ways I want to explain that you get sort of the entropy, the other entropy terms. As we showed earlier this year, this correlated very strongly with what sort of an independent study done before. And while this wasn't pre-registered, I didn't see the results before I had the full measurement. They correlate very strongly with what a panel of scientists had rated being the likely the probability that these studies will replicate and the relative effect size that they estimated. Now, the latter, as I argued before, is, I think, the appropriate measure of reproducibility. So it's encouraging that it correlates even better with K. Nonetheless, this seems at least to reflect how people perceive or evaluate evidence in a sense. Now, does that mean it actually reflects real reproducibility? Well, we won't know that yet for a little bit, but eventually there will be a pre-registered test of this. But from K theory, you can derive in a way that, since I know I'm already running slow, I won't describe at all, but you get from sort of a general statement about reproducibility to the stuff that you see off the bottom, where on the left-hand side, you have this measure of reproducibility that I think is the proper way to measure reproducibility, at least for certain meta-scientific purposes. And it's the one that I presented last year.
There's indeed 5 minutes left.
Thank you. And on the right-hand side, you see the sort of a distinctive prediction of the theory, okay, which is a linearity between this function of D of tau and reproducibility. And again, this will be tested more rigorously, presumably at some point later this year. But trying it out retrospectively on data from the many labs in social psychology and the Reproducibility Initiative in cancer biology, we have sort of some very encouraging results. Now, this is an exploratory result, but it's a very strong one. And it's all the more impressive because this wasn't even the way we did it for the studies in the Brazilian initiative. This was simply done by passing the text of the protocols. So devising a scheme and then just having an automatic passing in sentences, construct a tau of that, and measure d of tau. And it already works fairly well. This is not ideally what we should be doing, but it shows that there's something sort of impressive to measure there, which is independent of the p-value of the original studies and the square root of the sample size of the original studies, i.e. proxies of the statistical power of the original studies. So it's a completely independent factor that evidence would suggest that here we would need to take into account to really assess reproducibility. And just as a proof of concept, again, this is not sort of the real result that I would hope to see done, but this is where I should think meta-science ought to be aiming, is that once we are able to take these factors into account, then we are able to make, for example, more accurate comparisons between fields and forecast a particular field, what average reproducibility we should observe, and therefore be able to conclude maybe the data that we're observing is way below what we expect. There is a problem maybe with QRPs or other problems with research that will be discussed later today. We can't just say it straight away without taking into account the concrete diversity of fields we are looking at. All right, very quickly. Issue number 2, statistics, you'll remember, problems with fitting propensity that we can't measure. Well, it turns out that detail might actually help. And this comes from a pre-registered test. And this is a collaboration that I've started with Wes Bonifay, who produced the data I mentioned at the beginning about this problem. Oops. So basically, what we did is the following. Wes generated 20 structural equation models, all with the same number of parameters. I sort of, again, came up with a descriptive scheme, derived the d of tau, registered the predictions, and then Wes did his simulations and things to then see, how well the two predictions matched together.
There's
there's a lot of that we...
2 minutes left, Daniel.
Oh, yes. Well, I have 3 minutes on my counter, but...
okay, go.
Yeah, but in any case, results show the following, a strong negative correlation. So this, on the one hand, is the opposite of what we predicted, but on the other hand, it's, again, a very, very strong result. And there's no other explanation, right? There is no theory that would explain why d of tau should predict, in this case, as it happens, not model success in fitting data, but the model failure to fitting data. So this to me essentially was encouraging, if anything, because it shows that there's something that you can measure with these methods that no one else can measure, right? And it's meaningful. So iteration number 2 is a new descriptive protocol, okay, that does more justice to sort of the logic of structural equation modeling, perhaps. And lo and behold, now, this of course is now not a pre-registered test, but it works pretty damn well. I don't think it's the final method, actually. It still has limitations, as you can see. So there will be a pre-registered test on what will eventually might appear as a better method. But again, it shows that fitting propensity beyond the number of parameters can be measured about models. And why this is important? Because it's going to help us put a more severe test on theories. So just going back to the data from that I showed before, the two models that fit data very well that you see on the right-hand side are an exploratory factor analysis model, by definition atheoretical. On the left-hand side, you have a bifactor model, which are models used in all sorts of fields to test theories about IQ, stress, psychosis, or in clinical medicine quite a bit, because they have an appealing structure. But if they are so good at fitting random data, then of course, how many of these theories are actually not really supported? And this is where, sort of in a vision again of what might be the case in the future. The problem is that at the moment you're relying on these binary measures of fit that tell us nothing useful, or at least they're not severe enough. What we would be advocating is something along the lines of measuring the K of your theoretically informed model versus an equivalent exploratory model, and have trust in your theory to the extent that the former is larger than the latter. All right, so the key references are here about the sort of three bits of published things that I have so far. And concretely, just to summarize, what's missing in the current paradigm? There is complexity there, and we pretend it doesn't exist, or we pretend we can just brush it, just sort of model it away with a random effects. That's not the case. So what we really ought to be trying to do is being able to measure complexity in useful ways and integrate it in our evaluation of evidence. And I'm proposing a method to do so. This method has some promising support. Again, I'm still open to the possibility that there might be an entirely better way to do it. And if you have such an idea, I look forward to seeing develop it, or please get in touch and help me help you develop it. Thank you very much, and I look forward again to next talks and further questions.